sentiment. In any case, let's go ahead and get started. Well, it's not an exam, so no homework. No homework due tonight. But let's go ahead and talk about the last two quizzes of the semester. So the next quiz is going to be next Wednesday on November 18th to Thursday, November 19th. Covering lessons, just lesson 29, so today's lesson. And then the last quiz is going to be on Monday, November 23rd to Tuesday, November 24th, covering lessons 30 and 31. Now keep in mind this last quiz is actually going to be in that mini week right before Thanksgiving break, so just keep that in mind as you're planning your schedules. Just making sure you guys know that. Alright, well, let's go ahead and introduce the last sort of new unit relevant to exam material, or at least directly relevant to it, known as area and Riemann sums. So the first thing we're going to do is we're going to start out with some summation basics here. So we're asked to evaluate this first expression here, which is this summation from I equals 1 to 4 of I times 1 minus I squared. Now I might think, okay, well, you might have seen this before in high school, but if I haven't, well, what does this mean? Like, because I don't remember, like. So let's go ahead and do a quick little review or a crash course on it to see what's going on here. So what this says is that if we have the summation from I equals 1 to 4 of I times 1 minus I squared, well, let's see what this says. So we have this giant sigma here. So if you see this, that should indicate we have to add terms. So sigma notation means add terms. Okay, so that's all that means. And then if you see this I here, all that indicates is that that's what's known as an indexing variable. Index variable. And then if you see a 1 here, you have I equals 1. So in this case, that indicates to you that that's going to be where you start. So that's your starting value in this case. And this 4 on top indicates that's where you're ending. Ending value. Okay. And then this part here, the I times 1 minus I squared, that just simply corresponds to the general ith term. General ith term. Okay? Okay? So that's all that means. So to give you a rundown of what this means, here's what this says. So like I said, you're starting at I equals 1. So what that means is that if you're adding a bunch of terms, that means the first term you have to add is I equals 1. So if you let I equals 1 in this term here, you should have 1 times 1 minus 1 squared is what that means. Okay? So that's the I equals 1 term basically. So I equals 1 term. Okay? And then like I said, you basically keep adding, you're incrementing I by 1 until you hit 4, basically. So from there we say, all right, the next term we have to consider is the one that corresponds to when we let I equals 2. So we have 2 times 1 minus 2 squared now. So this would be the I equals 2 term. And then you increment by 1 again for I to get the I equals 3 term. So we get 3 times 1 minus 3 squared. So I equals 3 goes here. And then we keep incrementing by 1 for I each time until we hit this ending value. So in this case, we just hit, if we have I equals 4, this would be our I equals 4 term. And then, well, that's where our ending value is, so now we stop. So basically that's what that means. Okay, so from here, now we just go ahead and clean everything up. So this I equals 1 term, well, you should be able to pretty quickly see that's just 0, so no problems there. But now what about the next few terms? So if we let I equals 2 here, if we focus on this term, how does this numerical expression simplify? To clean this up a bit. Yep, just -6, right? Okay. And then we do the same thing with I equals 3, then we should have what? -24. And then you do the same thing with I equals 4 to get -60. Okay. So you add all these terms up, and this should get you -90 as your final answer. Okay. So that's example 1. So any questions on any of that? Okay. So now let's sort of work backwards with the next example. So in this case, we're given the summation, and we have to express it using this sigma notation as in this example, first example here. So we have to express this summation below for I equals 1. So that's our starting variable, our starting value. So we start here, and then we keep going until we hit n. So this is going to be where we end. So in this context, that should pretty quickly indicate to you what at least this part of the summation does. So we say, all right, that should give us that we have this summation, just this sigma thing, from I equals, in this case, we're starting at 1, and we have to keep going until we hit n here. So that's what that tells us. So all that remains is, well, we got to figure out what this general ith term is then. So let's go ahead and look at our summation to see what kind of ideas we can get from this. So in this case, if we sort of follow the pattern that the indexing variables give us here, then this should tell us, all right, well, this is the I equals 1 term. This is the I equals 2 term. Let me zoom in on this a bit. And then this should be the I equals n term. Okay? So taking a look at how we're writing this n I equals n term, let's see if we can use that to give us any clues as to how we can write the other 2 terms in a similar fashion. So one thing you'll note here is that what we're doing with this nth term here is that we're essentially just adding 1 to this and then raising it to the power of n. So let's see if we can write these first 2 terms in a similar fashion. So what you'll notice is that, well, with 2, well, that's just 1 plus 1. So 1 plus 1 raised to the power of 1. So 1 plus 1 to the first power. And then if we do a similar thing with the I equals 2 term, well, what you notice is that, well, we can write this in a similar fashion as, well, 2 plus 1 to the power of squared. And then plus dot dot dot. And then we keep going until we hit n plus 1 to the power of n. So in this case, we say, all right, well, this is the I equals 1 term. This is the I equals 2 term. And this is what happens to be the I equals n. So if we take a look at each of these terms here, we can say, all right, well, what would that tell us about what the general ith term is? Okay. So based off of the pattern that we're noticing here, it seems like the only things that really change are sort of this part right here, this number here, and then as well as this number here. That's the only thing that seems to change with each of these terms here. So taking that into account, what would that tell you about what form the general ith term has? Any thoughts or suggestions? Okay. So what you'll notice is that, all right, so if we let I equals n here, then we have n plus 1 to the power of n. If we let I equals 2, then we have 2 plus 1 to the power of 2. So in this case, like I said, the only thing that seems to change is this number here as well as this number here. So in this case, what that should tell you is that the general ith term should look like I plus 1 to the power of I. So in this case, your general your summation is then going to look like I plus 1 raised to the power of I. So that's going to be your example in this case. Right. So that's example 2. So any questions on that? Okay. So that's all I really wanted to say on summation basics. Now let's go ahead and see how we can, what's one useful application of this. So what you'll notice is that Riemann's, if we sort of apply this, one application that we'll be seeing in this lesson is Riemann sums. Now, Riemann sums are used to approximate area under a curve y equals f of x with n rectangles over an interval a comma b. Okay? So to see what I mean by this, since that was a bit of a mouthful, let's go ahead and apply this to a specific example to see what I mean by this. So one such example, which will more or less be the primary example of today's lesson, will be example 3, which states that we have to use left and right Riemann sums with n equals 3 rectangles to estimate the area under y equals x squared plus 1 on 0, 6. So you might think, all right, well, what does all that mean? So first off, let's actually sort of look at what we're trying to estimate first. So 1, 2, 3, 4, 5, 6. We'll go one more, 7. And then we put, so I'm going to have a little tick here because in this case we're estimating y equals x squared plus 1. So that means our graph is going to look something like this. So we have y equals x squared plus 1. Okay? So in this case we have 1, 2, 3, 4, 5, 6, 7. So essentially what we're trying to estimate here is the area from 0 to 6, so 0 is here, under y equals x squared plus 1. And in this case, the problem implicitly assumes we'll also have to be above the x-axis. So in this case, the area we're trying to figure out is this guy right here. Okay? So that's the area we're trying to figure out. So in this case, like we said in the example, we have to draw 3 rectangles near this curve. So here are the criteria they have to fulfill. So the big thing is that the base of rectangles must be on x-axis. Okay. So that's the first thing. The second thing is that you have to focus on sort of the width of each rectangle. So rectangles must have same width delta x. Now you might think, all right, well, what does that mean? So in this case, delta x is supposed to correspond to the width of your rectangle because we're ultimately trying to use rectangles to approximate this thing. So first thing we need is the width, and then we'll talk about the height in a second. But the first thing is that we say, all right, well, we break up our interval, which in this case is 0 to 6, into n equals 3 equal segments. Okay? So using this reasoning, we say, all right, well, what should that tell you about what delta x equals? So if we have to break up this interval of length 6 into 3 equal segments, what should that tell you about what delta x should be in this case? It'd be 2, right? Okay. And yeah, so in this case, one way to think of it is that, like I said, you take the interval, you take its length, and then you divide it by the number of rectangles you need. So I'm going to write it in this form for reasons that you'll see in a second. Because, in general, the delta x you need is the length of the interval, b minus a, and then you just divide that by n. Okay? So what that tells us is that, all right, well, that means the first rectangle has to quote unquote sits on 0, 2. So the first, that's the first rectangle, the width of that's the way the first rectangle has to sit. The second has to sit on 2 to 4. God, that's adult family now. And then the third on 4 to 6. So like I said, we have 3 rectangles, one of which sits on 0 to 2, the second on 2 to 4, and then the third on 4 to 6. So that's that part. And then that basically gives us the idea of how to find the width of our rectangle. Now let's figure out how to find the height of it to get the corresponding area. So the height of rectangle depends on f of x. Okay. So for left, I'll say respectively right, Riemann sums on sums. We have to use the f of x value at the left, or respectively right, endpoint of the base of each rectangle. Okay? Okay. So you might think, all right, well that seems, again, like a lot of words here, so how do I translate that into math that I should be caring about with the homework? Well, that's where the next page comes into play. So, so the left Riemann sum, let's take a look at the left Riemann sum first to get an idea of what I mean by this. So in this case, I'll draw the same graphs that we had before. So this is still y equals x squared plus 1, and this is still y equals x squared plus 1 here. So in this case, we say, all right, well, we have 0 here, 2, 4, and then we got 6. And then I'll do the same thing with this part here. So we have 2, 4, and then 6. So here's what we have with the left Riemann sum case. So like we said before, we have the left Riemann, for left Riemann sums, we have to use a function value at the left endpoint of the base of each rectangle. So in this case, if we focus on the interval 0 to 2 first, what that means is that the height of our rectangle depends on the function value at the left endpoint of that interval. So in this case, we need to figure out, well, f of 0. Okay? Since in this case, our function is f of x equals x squared plus 1. So the first rectangle is just this guy right here. So R1 is going here. The second rectangle is going to depend on the function value at the left endpoint of 2 to 4. So in this case, you need to figure out, well, the function value at x equals 2. So in this case, the height of this rectangle here is f of 2. And then for the third rectangle, you need to figure out the height of you figure out the function value of f of 4 for 4 to 6. So you can figure out the desired area from that. So in this case, this would be your R2, and this would be R3. So R for rectangle, of course. So okay. So now let's go ahead and figure out the left Riemann sum from this. So in this case we have, all right, so like I said, this is f of 0, this is f of 2, this is f of 4. So the left Riemann sum in this case is, well, we have to take each area of each rectangle and then add them up. So we have A of the area of R1 plus the area of R2 plus the area of R3. Okay? So in this case, we have, all right, well, the area of R1 is just, well, the length slash, so we have the length of it, which is 2, times the height, which is f of 0. Okay? And then similarly for the second rectangle, it's, again, 2 times the height, which is f of 2. And then for the third rectangle, we have 2 times f of 4. Okay? So in this case, like we said, f of x is just x squared plus 1. So we have 2 times 0 squared plus 1 plus 2 times 2 squared plus 1 and then plus 2 times 4 squared plus 1. Okay? So if we go ahead and clean this up a bit and simplify as much as we can, what numeric value do we get out of this? You can use the calculator if you need to.
That's 46.
Yep, I got 46 as well. Good. Okay. So that's the left Riemann sum. Now let's see what happens for the right one. So now in this case, if you want to figure out the area of the first rectangle, well, the length is still 2, but in this case, now you need to focus on the height. You need to focus on the function value at the right endpoint this time. So in this case, the height is going to be, in this case, f of 2 because of the fact that the right endpoint is 2. So that gives you that. For the second interval, we have, all right, well, we need to focus on the right endpoint of 2 to 4 if we need to figure out the area of that rectangle. So the height of that rectangle is then going to depend on f of 4 now. And then for the interval 4 to 6, we need to figure out the function value at the right endpoint. So in this case, f of 6. So f of 6. Okay, that's better. All right. So what that tells us is that, all right, this is f of 4. This is f of 2. So in this case, if we want to figure out the right Riemann sum, well, we still have to add up the areas of each of these rectangles. So we have a sub r1 plus a sub r2 plus a sub r3. If we denote this as r1, this is r2, and this is r3. So in this case now, what would if we focus on the area of the first rectangle, what would that be? Using similar reasoning that we had before. So in this case, we still have width 2, but then we have to multiply that by the height, which is what? 2, right? And then for the area of the second rectangle, what would that be? Yep, 2 times f of 4, and then, or I guess someone else.
2 times f of 6.
Yep, 2 times f of 6. Good. Okay, and then again, f of x is still x squared plus 1. So if we plug this into our function and then simplify as necessary, we should end up with 118 as our right Riemann sum here. Okay? So any questions on that part? Okay, so now you might be thinking, well, I'm pretty sure that you did this really simple example, Tim, but I'm pretty sure there are going to be a lot more complicated functions on the homework with n equals however many rectangles to be some extremely large number. So doing these kinds of computations is going to be really annoying. So how can I generalize this? So thankfully there is a way to do that. So to add the area of each rectangle, well, like I said, you're going to need both the height as well as the width. So we already established what the width is, so that's just delta x is just equal to the length of the interval b minus a divided by n. So that's the width, but to find the height, we need to figure out something a bit more. So for the height, we have to consider this new variable, which I'm going to denote as x sub I. So we have that's equal to a plus I times delta x for I equals 0, 1, 2, and then keep going until you hit n. So you might think, okay, well, and then where we have a comma b, this is our interval, and n rectangles. So, okay. So like I said, delta x is just the length of this interval divided by n, and then x sub I is just a plus I times delta x here. Okay? So you might think, all right, well, how can we interpret this x sub I thing we've established? So one way you could think of this is that this is just I steps of length delta x past a. Okay? So if we focus on the first few values of I, for instance, then we should have x sub 0 is equal to a, because if you let I equal 0 here, then that's just 0. So this, all you're left with is just a here. Then x sub 1 would then just be equal to, well, you let I equal 1 to get a plus delta x. Then I equals 2 gets you a plus, well, in this case, 2 times delta x, because I equals 2 now. And then you keep going down the line. Okay? So in this case, we say, all right, if we focus on x sub 0, well, that's basically 0 steps past a, so that's just a itself. X sub 1, you're basically you're basically focusing on one step of length delta x past a, so you're adding one factor of delta x to a. X sub 2 says, all right, now I have to add 2 increments of delta x to a to get x sub 2, and then so on and so forth. So in other words, what that will give you is that the height of ith rectangle is then equal to the function value at x sub I. Okay? So then if I just multiply delta x to that, that'll give me the corresponding area I need. So area of ith rectangle is then just, well, multiply delta x to our height to then get the area of the ith rectangle. Okay? So in this case, if we want to generalize the Riemann sum formulas, then what we'll need is the sigma notation we introduced at the start of the lesson. So in this case, the left Riemann sum is then the summation from I equals 0 to n minus 1 of delta x times f of x sub I. Right? So one thing you'll notice is that, well, delta x is just essentially just some number added to each f of x sub I. So in this case, you can rewrite this as delta x times, if you wish to expand this out, we have f of x sub 0 plus f of x sub 1 plus f of x sub 2, and you keep going until you get to f of x sub n minus 1. Okay? Now, for the right Riemann sum, the general ith terms are the same. So, in other words, you still have the summation of something from delta x times f of x sub I. But in this case, you're starting with I equals 1 now, and you're going to keep going until you hit n. So, in this case, we have delta x times, in this case, f of x sub 1 plus f of x sub 2 plus dot 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 plus f of x sub n minus 1 plus f of x sub n. Okay? So that's basically what the left Riemann and right Riemann sums give you in this case. So, any questions on that part? Okay. So, to give you a better idea of what these formulas mean in this context, let's go ahead and apply them to the example we just did, to sort of give you an idea of what's happening. So, in this case, we say, all right, well, if we apply these formulas here to the above example, yields, all right, so if f of x equals x squared plus 1, we had on 0, comma 6, then we said, all right, well, we had, what was it? We had n equals 3 rectangles, and as we established before, delta x is just equal to 2 now. So what that should tell you is that x sub I, therefore, is then equal to, well, a, which in this case is just 0. So we have 0 plus I times delta x, which in this case is just 2. So in this case, you just have 2I is your x sub I value. So then, like I said, this is going to be for I equals 0, 1, 2, and in this case, you keep going until you hit n, which in this case is just 3. Okay, so if you want to plug them into the summation here, then your left Riemann sum then becomes the summation from I equals 0 to, in this case, n minus 1. So since n is 3, that should pretty quickly give you got to stop at 2 now. So in this case, you have delta x, which in this case is just 2, and then times f of, in this case, x sub I, which in this case is just 2 times I. So that will be your left Riemann sum, and then similarly, your right Riemann sum, your general ith terms would still be the same, so you still have 2 times f of 2i as we had before. But in this case, you're starting at 1 with the right Riemann sum, and you keep going until you hit n, which in this case is just 3. Okay? So now we say, all right, well, if you want to use this version of the left Riemann and right Riemann sum formulas, you can do that. That's fine. But it might help to figure out what these x sub I values are first for I equals 0, 1, 2, and 3. So let's go ahead and draw this little table here to do that. So we have I equals 0, 1, 2, and then 3. So like I said, so in this case, x sub I is now just 2i here. So if you let I equals 0, for instance, then what should that tell us about what x sub I is equal to? So if x sub I is 2 times I, then if you let I equals 0, what is x sub 0 equal to?
0.
0? And then if you let I equal 1, we get 1. Two, and then I equals 2 gives you 4, and then Yep, 6. Good. Okay, so what that tells us is that with the left Riemann sum, we have to say, all right, we have to multiply delta x to every function value. So in this case, we only care about going from I equals 0 to 2 here. So in this case, we only care about the function values at these 3 points here. So we have f of 0 plus f of 2 plus f of 4. So we have that, and then because we already have because we already computed this above, that's just 46. Now for the right Riemann sum, it's similar, except now we just need the last, in this case, last 3 terms here. So we have 2 times f of 2, we're so close, don't fail me now. It's 2 times f of 2 plus f of 4, and then plus a function value at x sub 3, so 6. So all we have to do is just add these, in this case, n equals 3 function values together to get the right Riemann sum, which again we already computed above to be 118. Okay? So that's basically how we can apply these formulas here to the example we just did. So again, sort of multiple ways of seeing the same problem essentially. So, okay. So again, I know there's a lot of expository things we just did basically in the past 35 minutes essentially, but are there any questions on what we just did? Because again, I know there's a lot of expository stuff that I kind of just threw at you. So, okay, then I'm just going to keep going then. So let's move on to our last example. So in this case, we have to use left and right Riemann sums with, in this case, n equals 4 rectangles to estimate the signed area under y equals 3 times cosine of 2x on the interval pi over 2 to pi. Now you might think, well, what does signed area mean? Well, in this case, you're basically just doing the same thing that we did above, but signed area basically just accommodates for when you have a negative function value on your interval. So f of x is less than 0 somewhere on a comma b. Okay, so that's all that means. So now let's go ahead and apply the formulas that we established above here to figure out the thing we need here. So in this case, let's go ahead and start by figuring out delta x. So like I said, that's just the length of this interval here divided by n equals 4, the number of rectangles we need. So in this case, we say, all right, well, in this case, a equals pi over 2 and b equals pi, and, well, n equals 4 as we just established. So that should tell you that delta x then should equal what from this? What would delta x equal? Okay, so let's go ahead and do that. So we already have b and a, so that's just, we have b, which is pi, and then minus a, which is pi over 2. And then you have to divide that by the number of rectangles we need, which in this case is just 4. So if we clean this up a bit, then we should end up with what as our delta x in terms of pi?
Pi over 2 divided by 4.
Yep, pi over 2 divided by 4, which simplifies to pi over
8.
Yep, pi over 8. Good. Okay, so that gives us delta x, no problem. So then now let's figure out what the x sub I is equal to. So like I said, a is just pi over 2 here. So we have pi over 2 plus I times, well, delta x, which in this case is pi over 8. Pi over 8 So in this case, for I equals, well, we have to keep going. We have to start at 0, and then we keep focusing on every value of I until we hit n, which in this case is just 4. So that means we have I equals 0, 1, 2, 3, and 4 is basically what that tells us. Okay? So taking that into account, let's go ahead and draw a similar table that we just established above. So, by which I mean this table right here. Okay? So in this case, let's go ahead and draw our 2-row chart. So we have I and x sub I. So we have 0, 1, 2, 3, and then 4. Okay? So if we focus on x sub I here, and if we let I equal 0, well, that should pretty quickly get you that x sub 0 is just 1. Just 0. So if I equals 0, then... So if this is 0, then this whole thing goes away, right? Just pi over 2. Okay? So now let's let I equal 1. So in this case, you should end up with pi over 2 plus pi over 8. So in this case, x sub 1 should then equal what, if we simplify that down a bit? So pi over 2 plus pi over 8 is what fraction times pi?
5 pi over 8.
Yep, 5 pi over 8. Good. So now if we let I equal 2 here, we say, all right, this is just pi over 2 plus 2 times pi over 8, which is just pi over 4. So if we add these two terms together, we should end up with what fraction times pi? Yep, 3 pi over 4. Good. Okay. And then you do a similar thing with I equals 3 and 4. So we have, in this case, pi over 2 plus 3 pi over 8 with I equals 3, which is then just 7 pi over 8. And then with I equals 4, you have pi over 2 plus pi over 2, which is then just pi. Okay? So that's the table you're going to need here for our example. So in this case, we say, all right, the left Riemann sum says, okay, we need to focus on the delta x, which in this case is pi over 8, times the sum, basically taking the first, in this case, 4 x sub I values, the function values of each of these 4 x sub I values, and then adding them up. So in this case, we have -3 times cosine of 2 times, because our function is this, 2 times, in this case, pi over 2, and then minus 3 times cosine of 2 times, in this case, 5 pi over 8, and then minus 3 times cosine of 2 times 3 pi over 4, and then minus 3 times cosine of 2 times 7 pi over 8. Okay? So like I said, I'm just taking the first 4 x sub I values here, I'm plugging them into -3 times cosine of 2x, and I'm adding these all up. So in this case, you can think of this as the I equals 0 term, I equals 1 term, I equals 2, and then I equals 3. Okay? So at this point, let's go ahead and clean this up a bit just to see where things land. So we have pi over 8 times -3 times cosine of, in this case, 2 times pi over 2. So that pretty quickly simplifies to pi, no problem. Minus 3 times cosine of 2 times 5 pi over 8, which simplifies to 5 pi over 4. and then minus 3 times cosine of 2 times 3 pi over 4, which is just 3 pi over 2. And then minus 3 times cosine of 7 pi over 4. Okay? So what do we notice from this? So we have pi over 8 times, well, first off, what is cosine of pi equal to? Does anyone remember cosine of pi from the unit circle? Yeah, just negative 1, right? So that means this whole term here becomes positive 3. Okay? And then we have minus 3 times cosine of 5 pi over 4. So what is that from the unit circle, if anyone remembers? Okay. Yeah, that one's a bit of a one we haven't really seen much of recently, so I'll go ahead and remind you. So cosine of 5 pi over 4 is just negative root 2 divided by 2. Okay? Then we have cosine of 3 pi over 2. So what is that one equal to, if anyone remembers that one? Okay. So in this case, that one's just a big fat 0. So this just becomes 0 here. And then minus 3 times cosine of 7 pi over 4, which in this case just becomes positive root 2 over 2. So what you'll notice is that, oh, wait a minute, these two terms here, this term and this term, these just cancel out no problem, right? So all you're really left with is just a 3 here from this term, first term here. So you're ultimately just left with 3 pi over 8 for your left Riemann sum. So that's the left Riemann sum. And then the right Riemann sum is going to be similar, except in this case, instead of focusing on these first 4 values of x sub I, now we only care about the last 4. So what I mean by that is that we have, now for the right Riemann sum, we have pi over 8, and we have negative 3 times cosine of, in this case, now we start with this term here. So now we have cosine of 5 pi over 4, because that's what this first term simplifies to. And minus 3 times cosine of 3 pi over 2. Minus 3 times cosine of 7 pi over 4. And then, in this case, minus 3 times cosine of, well, 2 times, in this case, x sub 4, which is just pi. Okay? So like I said, this is the I equals 1 term, I equals 2, I equals 3, and then I equals 4. Okay? So in this case, like we said, in this case, well, the I equals 2, that just still corresponds to 0, so that cancels out. And as we already established above, the I equals 1 term and I equals 3 term cancel each other out. So ultimately, you're just left with negative 3 times cosine of 2 pi inside here. But remember, what is cosine of 2 pi equal to? Does anyone remember cosine of 2 pi? That's 1. Good. So in this case, since cosine of 2 pi is just 1, that means you're ultimately just left with negative 3 pi over 8 for your right Riemann sum. Okay? And that's lesson 29. Okay, so any questions on all that? Like I said, I know there was a lot we threw at you today, but yeah. Okay, well, I guess I'll go ahead and see you all on Monday. Have a good weekend. And enjoy your nice, exam-free, well, at least for this class weekend. Other than that, I'll still have my office hours on Monday, and yeah, I'll see you all next week.